Hello everyone, in lecture 62, we will discuss a phasor form of the circuit constraints. At the end of last lecture, we've asked a question that can we use phasor to list the algebraic equation with complex coefficient directly instead of listing ordinary differential equation and then converting it into algebraic? As we know, listing the equation of a circuit needs two constraints, topological and element. In this lecture, we will discuss the phasor form of topological constraint and element constraint, which are suitable in time domain and the phasor domain. Let's focus on the topological constraints first. Topological constraints contain KCL and KVL. If all the time domain currents are transformed into their corresponding phasor forms, the phasor form of KCL can be written as the sum of all current phasors flowing to a node equals 0. Similarly, if all the time domain voltages are transformed into the phasor forms, the phasor form of KVL can be written as the sum of all voltage phasors in a loop equals 0. They are the phasor forms of KCL and KVL, which are topological constraints of the whole circuit. These are linear algebraic equations of phasor I and phasor U. Then we discuss the element constraints. The first element is resistor. In time domain, ut equals R times it. We transform U and I into the phasor forms. Then we get phasor U equals R times phasor I in the phasor domain. It's still a linear algebraic equation of U and I. We can draw its equivalent circuit in the phasor domain, in which there is R, phasor U, and phasor I. It's a real coefficient relationship between U and I, so phasor U has the same phase as phasor I. Next, we discuss inductors. The phasor form of the voltage of inductor is phasor U. The phasor form of the current of inductor is phasor I. So the differential of inductor current is j omega time phasor I. The differential relationship between inductor voltage and current is phasor U equals j omega time phasor I in phasor domain. It's an imaginary coefficient relationship between the voltage and the current. According to the equation, we can draw its equivalent circuit in the phasor domain. As long as L is transformed into j omega L, the equivalent circuit satisfies the equation phasor U equals j omega time phasor I. In other words, the inductor can be regarded as a resistor with imaginary coefficient. This is a phasor form of the inductor current. According to the definition of rotation factor J, J time a phasor makes the phasor rotate 90 degrees counterclockwise. So phasor U leads phasor I 90 degrees. You must remember this important conclusion. Besides, we can find the part of omega L represents the block function of the inductor to the current. In order to differ from the block function of the resistor to the current, we call it reactance. The reactance is caused by inductor, so it's called the inductive reactance. And we can find that the inductive reactance is a function of the angular frequency. We can draw the characteristic curve here. Inductive reactance increases linearly with the increase of angular frequency, which means when the frequency is 0, an inductor is a short circuit in sinusoidal steady state, and when the frequency tends to be infinite, the inductor reactance tends to be infinite. Next, let's analyze capacitors. Due to the dual relation between capacitors and inductors, the conclusions which are suitable for inductors are also suitable for capacitors. By transforming the current and the voltage into their phasor forms, we get du over dt corresponds to j omega times phasor u. So the imaginary coefficient relationship between the capacitor voltage and the current is phasor I equals j omega c times phasor u. The equation is often written as phasor u equals phasor I over j omega c, or minus j times 1 over omega c times phasor I. Similar to the discussion on inductors, minus 1 over omega c is called the capacitive reactance. The part of 1 over omega c represents the same block function as the inductor. In order to differ from resistor, we call it reactance. The minus sign here means that it's different from the inductive reactance. So you must remember that capacitive reactance is minus 1 over omega c. It's an imaginary coefficient relationship between the voltage and the current. Similar to the inductor, its circuit model in phasor domain is like this. In this model, the capacitor is transformed into a resistor with an imaginary coefficient. This is a phasor of a capacitive voltage. According to the function of rotating factor J, we know that the phasor of capacitor current leads phasor U 90 degrees. You must also remember this important conclusion. Next, we will draw the characteristic curve of capacitive reactance with change of frequency. Because capacitive reactance is negative, it's written in this form, absolute value. When the frequency tends to be 0, the capacitive reactance tends to be infinite. When the frequency tends to be infinite, the capacitive reactance tends to be 0. This is a reciprocal curve.